Good afternoon, everyone. I'm Brad Richardson. I am from the Flight Sciences Laboratory Computing Center at NASA's Johnson Space Center. This is a collaboration with my colleagues Darby and Shazeb. Some of you might know Shazeb from his work on E4S. His experience on that project was actually influential in our approach. Disclaimer, AI was used to help create this presentation, but all of the work described was performed by humans. Today, I'm going to take you on a journey. Our journey using spack to build and manage the entire software stack for our HPC clusters. We've got 4 compiler suites, 3 MPI implementations, over 1,000 installed packages, and a lot of stories to tell. Like any good journey, it had challenges, companions, and a few flying monkeys. So let's get started. Maybe. Eventually. There we go. All right, so let's set the scene. Before spack, everybody knows our software stacks were built the old-fashioned way, RPM packages where we could, manual builds where we couldn't, and it worked sort of for a while. We maintained 2 clusters at the FSL. One runs an InfiniBand network and one that's just running an Ethernet network, both HPE clusters with Intel chips. They both need effectively the same software stack, and they both kind of want it maintained and optimized. The process was, somebody builds a package, figures out the dependencies by hand, gets it working, documents it, maybe, moves on to the next one, multiply that by dozens of packages across 2 clusters, and you've got a full-time job just keeping the lights on. It was tedious, it was error-prone, tribal knowledge lived in people's heads, or worse, in undocumented shell history, but it worked for a little while, so we lived with it. And then the systems needed major OS upgrades, and we have to build everything from scratch, and that's when we realized we can't do that the old way. So what exactly was the problem? Here's the math. We support 4 compiler suites, GCC, Intel, NVHPC, LLVM, with 9 to 12 total versions across all of those suites. We have 3 MPI implementations, OpenMPI, MPitch, and MPT. We got about 60 packages that you really only need one version of, stuff like command line tools, like Git, CMake, Pandoc, DOS to Unix, whatever, stuff you only need one version of. But users know that we have multiple compilers and multiple MPIs, and they start asking to try out their project with the different ones. But they have some dependencies that also need to be built with those compilers and MPIs. And pretty quick, you've got around 20 packages that need to be built for every compiler times MPI combination. That's roughly 20 packages times 10 compilers times 3 MPIs, potentially 600 builds just for the matrix packages. And the single build packages, the compilers themselves, the MPIs, all the dependencies. Our installation ends up with over 270 root specs and over 1,000 total installed packages, and that is not something you can do by hand. And so that's the tornado that swept us out of Kansas. So the tornado dropped us into a new world. When our clusters needed a major system upgrade, we realized the old approach, the manual builds, the RPMs, the painstaking dependency management by hand wasn't going to survive the landing, and rebuilding the entire software stack manually was impossible. So we made the decision, we're not going to rebuild everything from scratch. We're going to do it right this time. We'll use a real package manager. We didn't just install this on Monday and have everything working by Friday, but the decision that we definitely weren't going to do it manually anymore, that was what got us out of Kansas. And like Dorothy, the first thing we needed to do was find the right pair of shoes. For those of you in the room, I probably don't need to explain what spack is in great detail, but we'll frame it the way we looked at it when we found it. We had this enormous combinatorial problem. We needed a tool that could handle all of that complexity, one that understood compilers, variants, and how to build the same package 10 different ways and keep them all organized and accessible. Spack is that tool. It's a package manager designed from the ground up for HPC, handles the full matrix, builds everything from source with complete configurability. You go, I need HDF5 with GCC 12 and OpenMPI 4, and also with one API and MPitch, and it does that. But, and this is important, just having the Ruby slippers doesn't mean you know how to click your heels yet. We had a long road ahead of us before we got home. Knowing that Spack could solve our problem and actually making it solved our problem turned out to be two different things. So let's start down the yellow brick road. So we weren't the first people to walk down this road, and we didn't have to walk it alone. One of the things that made Spack viable is, beyond the tool itself, the community around it. There's a vibrant ecosystem of HPC centers all over the world using Spack to manage their software stack, and many of them are very generous with their time and knowledge. The Spack Slack workspace is invaluable, great place to keep up with what's happening, ask questions, see how other sites are solving problems, and if you're not already there, definitely go join. I'll acknowledge our team member Shazeb, who was formerly one of the primary maintainers of the E4S Spack stack, which, for those who may not know, is one of the largest and most comprehensive Spack managed software deployments in the HPC world. Shazeb brought a wealth of experience and ideas to our approach, and many of the strategies I'll describe, particularly the use of CI for building and how we organized our configuration, that trace back to patterns that Shazeb developed while working on E4S. So I've also got talks from him linked here. We didn't figure all of this out in isolation. We stood on the shoulders of the community. And many of you in the room are fellow munchkins and have walked down this road before. So now with the help from the Lollipop Guild and our slippers on, here's the road we set out to follow. We had our tool, the Spack, we have our community, we need a plan. And it looked pretty on paper. So step one, define all your packages in Spack environments. Just declare what you want, variants, versions, etc. in the spack.yaml files. Concretize, let Spack solver figure out the dependency graph, all the things you need. Then build and install, let Spack automate the whole build and install process with all the right compilers and flags and dependencies, etc. Generate an LMOD hierarchical modules. Spack has built-in support for that. It creates the module files organized by core, compiler, MPI levels, kind of what you would expect. Expose it all to users. They run module avail and see clean, organized module tree. They load what they want, and they're done. And finally, we'll wrap it all into GitLab CI, so we're not doing any of this by hand. So a straight road, shining city at the end. Looks simple, right? What could go wrong? This is about one of our important design requirements. Our users don't need to know Spack exists. That's our goal. Our users just use the installed software through LMOD, and they don't have to care about Spack. In practice, that means they load GCC, and then they can see what's built with GCC. They load an MPI implementation, and they see what's built on top of that, etc. That's the idea. At no point do they need to run a Spack command. They don't know what a spec is. They haven't heard of the concretizer. We want our sysadmins to be like the wizard. Pay no attention to the sysadmin behind the curtain, frantically wrangling the YAML files and Spack commands. So we set off down the road with our pretty plan, six-step straight road, Emerald City gleaming on the horizon. Then we got to the haunted forest, and the trees started throwing apples at us from the shadows. I'll give you an overview of some of the things we ran into before we get into the specifics. First, swarms of errors, the concretizer conflicts, build failures, mysterious error messages, pointing you in the wrong direction. Every time you fix one, it feels like two more appear. And sometimes the concretizer doesn't even give you an error, it just hangs. Second, the compilers. You can't build a package with a compiler that Spack hasn't installed yet. But the compilers are packages, so there's a bootstrapping sequence you have to get right. Concretization at scale. When you throw 270 plus root specs at the concretizer with all their compiler and MPI combinations, the constraint solving problem becomes huge, and the concretizer slows to a crawl or just stops. Last, debugging. When something fails deep in a dependency chain in one specific compiler MPI combination, out of dozens, finding the root cause can be painful, error messages are often cryptic, and the feedback loops are long. And finally, the build times. A full scratch build of our entire stack takes over 12 hours. Even with the build cache, we were still looking at like 2 to 3 hours, and that means every iteration is slow. Every debugging cycle costs hours, sometimes a day. And so I'll walk you through some of the specific issues that, that we dealt with. So let's start with the flying monkeys. If you've worked with spack at any real scale, you know the feeling. You write your spack.yaml, you run spack concretize, and you get an error, you fix it, concretize again, different error, you fix that. And now a different package has a conflict. Every time you swat one monkey away, 2 more swoop in. The concretizer errors in particular can be cryptic, although I understand they're getting better. You'll get a message about some unsatisfiable constraint. It'll point you to something that seems completely unrelated to the actual problem. The real root cause is buried 3 levels deep of dependency, and the error message gives you almost no help finding that. You end up reading through the output, trying to piece together what actually went wrong. Build failures can be their own special adventure. Something build fine with GCC and fails with one API, or it builds with OpenMPI but not MPitch. You get the idea. And when you've got 4 compiler suites and 3 MPI implementations and you're building every combination of all of those, the likelihood that you're going to run into one of those is pretty high. But the one that really takes the cake is when the concretizer just hangs. You get no error message, you get no output, you just wait forever thinking, is it stuck, is it gonna finish? Eventually, hours later, you kill it, and it's still an open problem. I've listed the GitHub issue there. And figuring out which package is causing it to hang, you just kind of like binary search your whole spec list. If I remove this half, does it still hang? Well, it takes an hour for me to find out. But eventually you can get through all of them. It's just a lot of trial and error. So let me tell you about a couple of particular monkeys that got us. We were setting up the MPI environment and getting OpenMPI to concretize, and the concretizer just didn't. It wouldn't do it. It gave us an error, but the error message didn't point to anything in particularly that was useful. And so we started digging, checked the compiler configurations, checked our external packages, variant preferences, etc., simplified the environment, reread other error messages, going down the rabbit hole, and hours later, finally looking at the diffs as the OpenMPI package PY file had been changed, finally found out that the legacy launchers variant was not available in OpenMP 5. So we had that in our packages, OpenMPI, I think it was require legacy launchers. So there it was. Not hard to fix, was very hard to find. I think my understanding is that spack has gotten better at telling you ahead of time, like, hey, this is not going to work. But at the time, this cost us a little while.
I don't think it actually. So we check whether the variant exists somewhere.
You do now.
We do now. But I still don't think it'll catch this because it exists somewhere.
Yeah.
So like in this concretizer is hanging because it's switching on some choice, some pathological optimization case between 4 and 5, I think. So
Well, this one didn't freeze, but the error message it gave was just, I can't give you OpenMPI 5. Okay, why? And then, Yeah.
Brad, you're assembling the entire software stack. You're doing what E4S already does. And would
we've-
it have
we-
been easier if you would have just contacted us and said, here, these are my requirements, let E4S assemble the whole stack, because we do it in a slightly different way.
Fair.
Start with a compiler,
Uh-huh.
ensure that it works with the spack environment.
Mm-hmm.
Next, we take the batch system, which is Slurm or
Yep.
some other, and get a first MPI variant working with that, with the hello world. Before we start with any package, once
Yep.
we have that working, then we go about building the packages. If you put
Yep.
20 things
Well,
in the beginning,
I'll get to this here in a second. We didn't end up with one environment, right? And we do have Shazeb on the team, so he knows how E4S is put together. But anyway, the next one, this was another interesting one. Boost, which many of you know is a popular C++ library, would not compile using the Intel compilers. The build fails somewhere inside of Boost's build system, and the error message is from Boost build system, not particularly helpful. And this isn't SPAC's fault, but we still needed to go, figure out what was wrong. So we dig in, find the root cause, wrote a patch, submitted it to the upstream SPAC Boost package recipe, and happily the patch was accepted. So this is one of those like happy reports, which is we got to contribute back to the SPAC ecosystem. We found something, fixed it, and contributed back. And now everybody who wants to build Boost with the Intel compilers can. We didn't just use SPAC, we made it better for everybody. And in my opinion, this is the next big horizon for SPAC, which is lots of users finding the as yet unwritten conflicts and either fixing them or at least documenting them, right? So that's the flying monkeys, the individual errors and bugs, but some of our changes were more structural. So this is obvious in hindsight, but it's a fundamental constraint that shapes the entire structure of our installation. You can't build packages with a compiler that SPAC doesn't know about yet. It's a classic bootstrapping problem. So we need GCC 12, 13, et cetera. All the other compilers and versions all depend on those compilers. So the very first thing you have to do is stand up a dedicated compilers environment that installs all those compilers. Once they're installed, then you can install subsequent environments referencing those compilers, and this is one of the fundamental reasons we couldn't just throw everything into a single monolithic environment. Even if the concretizer could handle it, which we discussed it can't, the bootstrapping order matters. Compilers have to come first. And this is the first hint of why we ended up with a multi-environment strategy. It's not just aesthetics, it has to be. The other environments come later as we hit concretizer scaling limits, and but this one was from the get-go. We have to deal with this one. Next, we initially did think about being ambitious with our environment size. Thinking fewer environments means simpler management, less sequencing to worry about, fewer moving parts. So we loaded up our environment with as many specs as we could, and the concretizer had other plans. When you put all of those root specs into one environment, even a large subset of them, the concretizer slows to a crawl, taking hours to concretize before even a single package is built. And sometimes it's not just slow, sometimes it hangs entirely. And that's the painful part, is when the concretizer hangs, you don't know which package is causing the problem. There's no diagnostic output that says, I'm stuck on this package. So the debugging strategy becomes remove some packages, either one by one or binary search or however you're going to do it, reconcretize it, and see if it finishes. Sometimes there's more than one causing it to hang, and that really makes it even more difficult. But that's part of the size of the problem that it's trying to solve at that point. And so The lesson was break the problem into multiple focused environments and do it in steps. The next thing is the build times. A full from scratch build of our entire software stack, all 6 environments, all 4 compiler suites, all 3 NPI implementations, takes 12 hours. So what that looks like in practice is you make a change to your config on Monday morning, you kick off a CI build, you go to lunch, you come back, it's still running. You go to a couple of meetings, you check again, it's still running. You go home for the day, you wake up Tuesday morning and open your laptop, and it failed at hour 11 because of whatever decided to go wrong that time. So you spend a few hours tracking down the problem, fix the one line, push it again, and you're back into the poppy field to take another nap. The build cache helps enormously, and I'll talk about that here in a couple of slides. With the build cache, we can get that down to 2 to 3 hours, which is a huge improvement, but even then, 2 to 3 hours as you're debugging is a long feedback loop. So you're not iterating quickly through this.
Need more runners?
I'm guessing some of the things I heard about today, like the parallelizing installation from the build cache, will make a big difference here. So I'm looking forward to trying that. So this is where we give the process a brain. When you have 6 separate SPAC environments that have to be installed in a specific order, compilers, base, MPIs, etc., you aren't doing that by hand, because if a human has to remember to run the right commands in the right order, filling in the right paths, etc., that's when mistakes happen, so we automated the thing. Our automation lives in GitLab CI. We have 3 distinct pipeline jobs that serve different purposes. First is the merge request build. This is the one we're using on a regular basis. You want to add a new version, add a new package, bump a version, change a variant. This job kicks off automatically and builds whatever's changed and pushes the results into the build cache. This is how you can kind of iterate. The second is we do a full from scratch rebuild that runs on a schedule, not every day, but regularly, once a week, once a month, something like that, which is, can we still build the entire stack from zero? Upstream packages change, new SPAC versions, compilers get updated, et cetera. And sometimes things that worked last week silently break, and so this from scratch build helps us know when things are breaking. It takes the full 12 plus hours, but it runs on a schedule, so that doesn't matter quite so much. And then the other is a production deploy, and this one is a manual trigger. At some point, a human makes the decision that a particular build is ready for production, and it installs from the build cache, so it's relatively fast, apparently will be faster, and it's reliable because you're just installing the exact binaries that we have already built and tested. So we're not rebuilding anything. And underneath all of these 3 jobs, we have got scripts that know about the environment sequencing. They handle all the progression of the different environments. This gives us our process of brain, basically. The build cache is the heart of the workflow, though, right? It's the binary artifact repository. You've all heard about it. And so, gets our build time down from the 12 hours to, at this point, 2 to 3, but hopefully less as we update SPAC. This is the difference between iterating once or twice or 3 times a week to maybe a couple times a day. Let's see. The multi-environment strategy. So first is the compilers, right? We've got to install our compilers. And then base, we've got around 60 packages that we really only need a single version of. Like I said earlier, things like CMake and Git. We just use one. We pick a compiler and we just build all of them with that particular compiler. MPIs, we've got the 3 MPI implementations that we use. But that's still 20 plus builds just for MPI. HPC libs, this is where the combinatorial explosion starts to take off. We're building libraries like HDF5, NetCDF that need to be built for every compiler and every MPI implementation. And this is where we really start to get into the big number of root specs. And fifth is our HPC apps. This is like the applications that our users care about, and for whatever reason want to make sure they've got one built with every version of compiler and MPI on the planet so they can test and see which one's fastest and yada yada. And then we've got a small 32-bit environment because for reasons we have legacy code that need to be built with 32-bit libraries. So we got that environment. And so one of the design decisions we made for this is that they do not reference each other using the spack upstreams or the include concrete, or I think it's called include environment now. We just rely on spack's built-in package reuse. We just set reuse true and it picks up whatever's already installed in the instance. And we're also using the build caches, so it's picking up stuff from the build caches as well. We also...
Did you use your own build cache?
Yes.
The E4S build cache already has 7,000 packages.
No, we're using our own because we're trying to be a bit more machine specific and optimize more for our specific machines. So pulling from the more generic build caches, we might not be as optimized. We might look into that at some point, but for now we're just creating our own. We also set compiler mixing to false. This one was important because without it, spack might decide to build a dependency with a different compiler than the package that depends on it, and we don't actually want that. Early on when we were trying to do this, it would make weird decisions about like, oh, this part of the subgraph will be built with that compiler. And so this kind of reunified it a little bit, yeah.
Is that true for the base packages? I mean, the base packages just be built with GCC and that's enough for
Yeah, for the base packages, we're just picking GCC 12. I mean, at this point, that's 12 is what we're using. And for the most part, it just goes... I think what we did was prefer GCC 12, and for whatever reason there, the concretizer's happy to just, yeah, GCC 12 works for everything and builds everything with the GCC 12. But what we would hit was like NetCDF built with Intel 1 API on top of MPitch would then pick HDF5 that was built with GCC 13 and OpenMPI. And you go, that doesn't, wait, what, why? So the compiler mixing flag helped. And then we also used the double % syntax to propagate the tool chains as the preference down as well when we're using the matrix specifications. So those things kind of really helped unify the dependency trees a little bit for us. I think if a package says like, hey, this is a conflict, then it's just a preference, so it will go, oh, well, then I will do what it says. But also, for some of the like kernel-involved stuff, we're just using the RPM builds and setting it external and letting it use those.
Yeah, with XPMet, you have to say XPMet or set GCC in your environment, even if you declare it external.
Okay. We haven't noticed any problems with that. So, and so for the environment configurations, you might think there's a whole spell book to get this working, but the actual Magic is a lot simpler than that. We just have a list of spack configuration files. They're split up using the include capability so that the bits of configuration that are common between them live in one place. and then some of them are just a bit templated. They contain a few placeholder variables like which system are we building this for, where to deploy it, whether to pad the install paths because we're going to put it in the build cache. And then we just use plain old sed to substitute the actual values for the target cluster environment, et cetera. We do this because we're trying to support the multiple different build modes, right? Are we doing a build or a rebuild or a deploy, as well as a few different options for testing. So rather than maintaining completely separate sets of spack configuration files, we maintain one set of templates and substitute the handful of things that differ just using sed. We were in a past iteration doing some more complicated stuff with like string interpolation in bash scripts that then get echoed to some files and then iterating over a whole series of spack commands. And some of that was necessary back like years ago due to some limitations for older versions of spack. But at this point, it's that like hierarchy of config files and just some simple search and replace. So sometimes the most powerful spells are the simplest ones. Let's see, where am I at? All right. And finally, there's no place like home. So after the tornado, the dark forest, the flying monkeys, and the poppy fields, this is what our users can see. It's just a simple hierarchy of LMOD modules. They just module load whatever they need, with it auto showing what's actually compatible or reloading what's compatible. So over 1,000 packages, 4 compiler suites, 3 MPI implementations, all built, tested, and the users don't need to know about spack. We finally made it home. So lessons learned, spack doesn't make everything easy, just to be clear. We showed you the tornado, the winged monkeys, all that. There's still some frustration, but an installation at this scale would not be feasible without spack. We couldn't do it by hand. You couldn't do it with RPMs. You can't do it with shell scripts. Spack makes it possible. Not easy, but possible. And at this scale, possible is the whole world. So what did we learn along the way? If we were starting a simpler effort, break the problem into pieces. Don't put all your root specs into one environment. The concretizer will not be happy about it. Invest in automation and CI early. Don't wait until you have everything working to automate it. Just automate it from the start. Use the build caches. They're not optional. They are essential, or you're not going to be able to iterate very well. Lean on the community. Go to the spack Slack workspace, attend the community meetings, and it's pretty good to have somebody on the team who's built one of these large environments before. Helps know where some of the sharp corners are. And then contribute back when you find a patch that needs to be made, when you find a combination of things that didn't build together, submit that back so the rest of us can learn from those. Spack has been a mature tool. It's not perfect, and I don't think anyone on the Spack team would claim that it is, but it's powerful, flexible, and improving. I've learned some new things that we're going to be trying out when I get back. So that's a huge deal. Genuine thanks to the Spack development team. Years of development, thousands of packages, and a thriving ecosystem. We're building our stack on top of all of your work, so definitely thank you. And that brings us to the end of the Yellow Brick Road. So, any questions?
Thanks. I think we have time for like one question while Alex gets set up. Hold on. Let me run out here and do this thing.
Did you have to force concretize, or did you just do concretize for these staggered or layered environments?
So the environments are independent, so you don't have to do a forced concretize.
Okay. And did you?
So the environments are separate, so you don't need a force concretize.
Okay.
But for some of the testing purposes, we are like reinstalling into the same spack instance, and in those instances, the automation is doing a force concretization.
And do you do the concretization with the mirrors enabled or with them, the build cache mirrors enabled or disabled? Or?
The build caches are enabled so it can reuse from there.
Yeah, well, we found when we were building packages on develop and it kept changing, we would get odd solutions coming out of the build cache.
Oh yeah, we still get really weird solutions on occasion.
And exactly. Pick a release, freeze, stack packages, whatever. That's what we've had to do.